All right, good morning. So, I promised you guys we were going to do an example of a test hypothesis, and that is just what we're going to do here. So, this is number 54 in your book, all right? And I'll go ahead and read this, although I think you should be able to see this off of the camera. So, we're going to say, making sure scales used by businesses in the United States are accurate is a responsibility for the National Institute of Standards and Technology in Washington, D.C. It says, suppose the NIST technicians are testing a scale by using a weight known to be exactly 1,000 grams. They weigh this weight on a scale 50 times and read the result each time. This sounds like an exciting job. The 50 scale readings have a sample mean of X bar equals 1,006 grams, and the scale is out of calibration if the mean scale reading differs from 1,000 grams. Okay. The technicians want to perform a hypothesis test to determine whether or not the scale is out of calibration. Okay, so let's go ahead and apply our 5 steps here and see if we can't solve this problem. Okay, so I'm going to go ahead and cover some of this so that I can reuse perhaps in a later date. But our first step is to say we have to set up our conflicting hypothesis. Now, this is a nice one because if the scale is too light or if the scale is too heavy, that's a problem on either side. So they want to say, is it different, right? Is it different than 1,000 grams? Okay, so it differs from 1,000 grams. So my mu is going to be 1,000, or it isn't. Okay, so that's how we have that. And then if you look down through the problem, it says state your conclusion and use the alpha equals 0.05 level of significance. I really get the habit of writing this alpha up here because it declares it at the beginning, and now we can't really change our minds about this, okay? And that was step 2. All right. Step 3, I'm going to use step 3 and 4 both on hand and with a calculator, okay? So step 3 is to calculate our test statistic. Okay, calculate our test statistic. And we're using sigma is known. Okay, so we're going to say, we're going to call this a z distribution. Okay, and the formula we're going to use for that is x bar minus mu divided by sigma over the square root of n. This is the same thing we had in chapter 7. We were talking about sample means. Okay, so it's the same formula. And we have to deal with the same assumptions. We're talking about central limit theorem. How do I know that this distribution happens to be normal? Well, they don't tell me, but I don't really care because how many trials do I need by central limit theorem? I need 30. And since 50 is a bigger number than 30, right, I know that this is going to be normal for us. Okay, I'm going to go ahead and write down the other things. The experimental weight that they found, right, that was 1,006. So 1,006 grams. My mu, they said the mu is 1,000. Okay, sigma, what did they tell us sigma was? Because they said sigma is known, otherwise we wouldn't be in this part of the chapter. Sigma is 2. Okay. So I have all the pieces I need to plug this into my formula, okay, and that's just what we're going to do. So we're going to say z is equal to, and I'll go real careful with my parentheses here, knowing that some of you may or may not have good calculators, but we have 1,000.6 minus 1,000 and parentheses, right? And then we have, and I'll put these in parentheses too, that's 2 divided by the square root of n is 50. All right, so great. Let's go ahead and see what we get with that. All right, so I'm going to go ahead and turn this on. All right, can we see that? Perhaps. Let's see here. Not okay. This is probably making it worse. All right, but let's go ahead and plug this stuff in. Okay, here's how we're going to do this. So we have 1,000.6 minus 1,000, okay, divided by parentheses 2 divided by the square root. Where's my square root function here? Right there under the squared. square root of 50 and parentheses and hit equals. Okay, and we get 2.12. That's a z-score. Okay, this z-score is equal to 2.12. All right, the calculator value that I get when we do it the second time is going to differ a little bit because I'm cutting this off to 2 decimal places. Okay, I'm cutting this off to 2 decimal places, but we'll go from there. Okay, because I'm using a 2-sample test, all right, we have to allow for the fact that we have a probability over here, but because it's a 2-sample test, we also have to allow for a probability over there. So whatever I find for this value here, I'm going to have to double it because I need both of them, okay? And this is going back to a Chapter 7 problem. This is going back to a normal distribution problem. I would like to know what is the probability that is above the z-score of 2.12. Okay, so we're going to go back to our calculators. Okay, normally I would have taught this with tables, but we're not doing that anymore. So we have second function distribution. We have norm CDF because we always use the CDF for normal distribution. Okay, and the low number is 2.12. The low number is 2.12. Okay, and then you have to use something relatively high for a standard normal distribution. Well, 10 is relatively high. 100 is certainly relatively high. If you want to use the 1 EE99, be my guest, but this is not going to change the outcome very much. And since it's a standard normal, I know that my mean is 0. All right, so the mean would be 0, and the standard deviation would be 1. Okay, and let's go see what that is. Okay, and we ended up with 0.0170. Okay, so this area here is 0.0170. Way back at the beginning, we talked about normal distribution and how it was symmetric, right? This side will fold over on that side. So if this area here is 0.0170, then what do you suppose this area is? Well, that's right. This is also 0.0170. Okay, and we have to add these two things up together. Okay, so my p-value, right, is 0.0170 plus 0.0170, and that comes out to a tidy 0.0340. Okay, 17 and 17 would make 34. All right. Okay, so this was step 3, calculate the test statistic, and step 4 would be calculate the p-value. Okay, now we have to compare. My cutoff for taking HO, my cutoff for saying that this is HO is 5%. This is under 5%. Okay, this would be called the rejection region here. Okay, we're going to say since the p-value is smaller than alpha, right? 0.0340 is smaller than 0.05. Okay, I needed this to get bigger than 0.05. I needed this probability to be larger than 0.05 in order to say, yeah, it's calibrated. But this is an unusual event, right? And unusual is defined by our standard here. Okay, so this is an unusual event. So say, look, this is not actually equal to 1,000. Okay, I know it's close, but we can notice a difference. And if we're setting the scale out, it's not calibrated. Okay, so my last one is since the 0.04 or 0.0340 is less than 0.5, we're going to say reject the null hypothesis, okay, which means the scale is out of calibration. Okay, so that's how you would do this thing by hand, or mostly by hand, at least doing the calculation by hand. But you know what? If you have a fancier calculator, your calculator will actually do most of this work for you. Okay, so I'm going to go ahead and put this back down here, and hopefully I'm completely in screen here. So what we're going to do instead, okay, is we're going to go to Stat, and we're going to go to Tests. And this one, you don't have to hunt for it. Z-test, it's right on top. This is exactly the one you're looking for. We'll just press input on that one. In this case, we are not giving it a bunch of data. We're not going. They didn't give us the list of all 50 weights. Thank goodness. So we're just going to go ahead and hit stats. Okay. our, we're back up here. Right, we're right there. Okay, my HO. Okay, let me go ahead and go back to this. My HO was mu was 1,000. So whatever the null hypothesis says, that's what you're going with. So my mu is 1,000. My standard deviation, they told us that that was 2. So standard deviation is 2. X bar was 1,000. Oops, 1,006. Okay. We have 50 for our values here, and we're going to go ahead and hit a two-sided test. Okay. Drawing takes a little bit long, but it is really nifty to see that. But if you don't, that's okay. But we're going to go. So how would you enter this in, for an answer that I would want you to have here? And I'll put that back in just a second. But you would say, I want to do a z-test, right? And we did mu 0 is equal to 1,000. We want standard deviation was equal to 2. We want x bar is equal to 1,006. We need n is equal to 50. And just to reiterate, although you will write it when you do a test of hypothesis, you will start with these 3 lines because that tells your reader, I'm doing a test of hypothesis here. Okay, you need that. Okay, and we're just going to say, mu is not equal to mu naught, just to tell me which section you wanted to pick in the calculator. All right, so let me bring that back. Notice we just went through all the different pieces that we entered in the calculator. You're just writing them down almost as an insurance policy to let me know that's what you put in the calculator. Okay, and then since we're on calculate, let's go ahead and say calculate and go what the answer is going to be here. Notice we have a z of 2.12. That's very similar to what we got. It's exactly what we got. Their p-value, instead of being 0.0340, theirs was 0.0338. 94 and keep going. This is what you get when you don't round it to 2 decimal places, okay? So they told us what the p-value is, and now it's still up to you, right, to engage your minds and say, well, is this a bigger number or a smaller number than 0.05? And if it's a smaller number than 0.05, right, then we're going to say, reject the null hypothesis. Oops, we're already out of frame. We're going to, since it's a smaller number than 0.05, we're going to say reject the null hypothesis and say the scale is out of calibration. Okay? Now, here's why I want you to declare your alpha at the beginning of the process rather than at the end. Say you were in a hurry and you did not want to recalibrate the scale. And you left it up to somebody to pick their alpha. Maybe your boss says, we got to get this out. I don't care if it's right, just get it out. And we change this to 0.01. Okay? Is my 0.034 a bigger number or smaller number than 0.01? Well, this is bigger. Since this was now our new cutoff, this is now bigger than the cutoff. Okay? So if we chose, I'm going to go back to my other paper there. So if we chose alpha to be 0.01, okay, since our p-value, 3.40, is now a bigger number than 0.01, we reach the opposite conclusion. We say, do not reject HO. The scale is in calibration. And say, sure, ship this thing out, okay? But that's not how science works. Science works like you establish what is your threshold, you do your experiment, and then you check whether your results meet or don't meet your threshold. If they don't meet it, then you're out of luck. You can say, well, that didn't work out so well. So be careful about this. I've never been in a position where I've had a multi-million-dollar pharmaceutical test and it didn't work. And then the boss comes down to my lab and says, are you sure you wanted the alpha to be 0.05? Are you sure you didn't want it to be 0.01? We'd really like to put this drug on the market. So I've never been in a position. I don't know what I'd do. I hope I do the right thing. I hope the same thing for you. Okay, but that's how you do a test of hypothesis. I'm going to put up a one-sided test in just a moment here. Okay, all right. Thank you and goodbye.